So our next speaker is Heidi Newberg, class of '87, physics. Professor Newberg is an astrophysicist who is best known for her discovery of small galaxies that continue to be cannibalized by the larger Milky Way galaxy. She contributed to the discovery of dark energy and the success of paradigm-shifting astronomical surveys, such as the Sloan Digital Sky Survey. She currently runs Milky Way at Home, a petaflops scale volunteer supercomputing platform that is being used to optimize models of the Milky Way. She was recently named a NASA NIAC Fellow for her design of a space telescope that could potentially detect Earth 2.0. Heidi.
See if I can operate this. So today what I want to get to is the whole point at the end of the talk. I want you to imagine the Milky Way galaxy as this dynamic organism that's interacting with itself, and that's what gives us the picture of the galaxy we see today. And you saw a little bit about that this morning with Yang Zheng's talk. And I also want, what I'm highlighting mostly is the advances in this field are being made here at Rensselaer, and so that's what I'm going to try to give you. So I wanted to start out by giving you a picture of the Milky Way galaxy just to get us started. Unfortunately, that's not a picture of the Milky Way. I could not find a selfie stick long enough to take that picture. So I have this picture of the Pinwheel Galaxy. And so when people think of the Milky Way galaxy, they're usually thinking of the spiral arms that we see like this and all the maybe a bar in the middle and that kind of structure. But there are many more parts to the Milky Way galaxy. This is a picture from a textbook that I think I used when I was an undergraduate student here. And it gives you the basic pictures of, let's see, does this have a? Yeah, we do have a basic picture of the Milky Way galaxy, and you see that the spiral arms are in this disk structure around here. In the center is a galactic bulge, and these days, we think those stars that are in the bulge in the center of the Milky Way are actually mostly bar stars, so they're not really part of a separate component there. The sun would be about here in the disk, and then I say there's also the supermassive black hole in the center of the galaxy. The supermassive black hole gets a lot of press. Everyone likes that supermassive black hole in the center of the galaxy. But from my point of view, it is 1,000,000 times more massive than the sun. But the Milky Way galaxy is 1,000,000 times more massive than that. And so I never really worry about that little thing in the middle that's doing whatever it does in there. And then out here in the outer parts, which we call the halo for some reason, I don't really know, there are these globular clusters out here, and globular clusters are like 1,000,000 stars, and they're old. And the stars that are in the disk are young stars. Now, there's some are older stars, but all the young stars mostly are down here. And then there are these globular clusters here with old stars there. And so when I was a student, my professor told me the Milky Way galaxy formed because this big gas cloud came and gravitationally collapsed to make the Milky Way, so it's pulling itself together. And because as it pulls itself in, like the ice skater, it wants to swirl around, it gets this disk of stars, because it can't get rid of that circular motion, and it comes in and you get this disk. And the globular clusters are the things that were left behind when that gas cloud collapsed. And I remember there in class thinking, that's really weird. How can it be that a big gas cloud collapses and it leaves behind 1,000,000 solar masses as it collapses? That doesn't make any sense. And so we're at a place in astronomy where you can probably sit out there and watch astronomers talk and think, oh my God, that doesn't make any sense. And then, 30 years later, maybe you'll find out you were right. So I want to show you, this is a modern day movie, I think Young showed you one earlier, of a universe, I just grabbed one off the web, that makes something that looks like the Milky Way galaxy. And you see that you start with over-densities in the early universe. They're a little colder and a little more dense, and they get gravitationally contracted together, and they make smaller things, which then merge with other things, which then merge with other things, and it comes in, and now you're starting to see that there's like a disk in there, and things are going, so this whole like motion of gravitational attraction of small things growing up to be bigger things in this hierarchical structure formation, and now I guess that's Andromeda coming in from the side. And the movie stops because you get to where we are today. But this is way different from that static picture of the Milky Way that I was taught. This is the disk, this is the halo, this is the, bulge in the middle. This whole thing is just an organism that interacts with itself. So, all right, here I have to navigate to there. All right, so I've been working in the Milky Way galaxy, which is the only galaxy we can really see in 6 dimensions, 3 dimensions of space and 3 dimensions of velocity. Actually, many more, because we have chemical compositions and all kinds of other things to look at. What we know now, and I'm not doing this all in chronological order of where we learned, but what we know now is that there are small galaxies that are in orbit around our Milky Way, and the blue is the disk on edge from our galaxy, so it's the disk turned on its side. And you can see that as a small galaxy goes around the Milky Way, the stars get pulled gravitationally off of that small galaxy, and the ones that get the inside track go out ahead, and the ones that are pulled off and get the outside track end up, being pulled behind into these big streams of stars. And so that, in that way, stars that are immigrants, they were born in some other galaxy, some small galaxy out there. They weren't born in our galaxy. The disk stars like the sun were, but these stars out in the halo were born somewhere else. And then the galaxy fell in, and it gets stripped out. And if you get a bunch of these things in the halo, then you build all those stars in the halo and all those globular clusters. And yeah, they're old, but they weren't formed here. That's why they come in. And so this is a simulation by one of my colleagues, Catherine Johnston, of the Sagittarius dwarf tidal stream. So by far the thing that I'm most known for in the science world, in Albany, I'm known as Amy Newberg's mother. But in the science world, I'm known for discovering that these streams of stars in the halo, in the outer parts of the Milky Way galaxy. And this is a picture of just looking up at the sky, and it's probably, I don't know, like 100 degrees across. So this is a big piece of the sky that's been surveyed by the Sloan Digital Sky Survey. And if you look up at the sky, you don't see these streams. We had to choose out the things that are most likely to be stream stars and plot those, otherwise you wouldn't see this beautiful picture. But you can see the Sagittarius stream spreading out across the sky, and then there's the Orphan stream, and there are all kinds of other, 100 streams have been found since the original one that are just all over the Milky Way halo. And I got to edit the book on this, so literally wrote the book. All right, so, but my students have also been working on things here at Rensselaer. Tom Donlan recently wrote his thesis on shell structures. So the dwarf galaxy you saw before was going kind of in a circle around the galaxy. If the dwarf galaxy falls in and goes straight through the center, then it completely disrupts, and then the stars go out and they have to turn around and come back, and then they go out and they stop and turn around and come back. And when they stop out there, they form these shells where it slows down, and so you build up stars right here at the shells at the edge. And then as time goes on, then you get more and more stars going out and turning around, and more turnaround points. And so the turnaround points get closer and closer together, and then it gets harder to see that they're shells, and there's a lot of them, and they're closer together. So Tom managed to figure out that you could date the time since this thing fell in by how many shells and how close they are together. And so he was able to show that this is, I don't know, maybe 1 to 3 billion years ago that the dwarf galaxy fell in and made these shells. And in fact, these are the first shells. This is the first time anyone has seen shell structure in the Milky Way galaxy. They'd been seen in other galaxies, but never been seen in ours, because in our galaxy, actually, I should have told you this before, you see that over, here, there's like this big cloud of stars. And so from inside the galaxy, you see it as a big cloud out there. And so he was able to explain what those things were. I had a visiting researcher from China, Xu Yan, who came out, and we were actually working on Sloan Digital Sky Survey data that had been public for 10 years. There's just a lot of public data out there, and there's a lot of information that people have not gotten out of it. And so we were looking at the densities of stars starting from the sun and looking outwards towards the outer part of the galaxy, and we noticed that there's more stars above the galactic plane, above the disk of the galaxy, when it's close to you, and then you see more below, and then you see more above, and then you see more below as you go out. And I showed this data to some of my colleagues that studied disks at that, because I wasn't really doing disks at that time. I showed them my colleagues who were doing disks, and they said, there's no way, there's nothing that would cause these motions in the up and down direction in a galaxy, because it's axisymmetric, It's axisymmetric. We don't even do our simulations in 3D, we do them in 2D. And so it took us a while to publish it, because it's always harder to publish a result that nobody thinks is right. But luckily, about the time we eventually did get actually, I'll tell you, this picture was $2,000. We got this, and so we paid $2,000 for the picture, so we got it into the Huffington Post when this came out. So, all right. Anyway, some of the theorists about the time we came up with this paper showed that dwarf galaxies, the same thing we were just talking about, dwarf galaxies are not axisymmetric about the disk, right? So they come in and they go through the disk, and just like a pebble in a pond makes ripples in a pond, these dwarf galaxies, the gravity from them makes ripples in the disk. And so so not only is the halo this, hive of stuff going on and falling in, that hive of stuff falling in is also affecting the disk of the Milky Way galaxy and causing these kind of ripples. But in addition to the ripples, there's all kinds of other substructure that can happen in the disk of the Milky Way. This is a simulation of Andromeda, and then there's going to be M32 is simulated going through. And you see, as that dwarf galaxy fell in through this disk, it formed a spiral structure. So even the spiral structure of the Milky Way is affected. It's not complete. I had a student who's working on this. I thought it would be completely because of, but it isn't completely because of. It's partially because of stuff that keeps stirring it by these dwarf galaxies falling in. All right. So I want to also talk a little bit about dark matter. Dark matter. Dark matter was something that people started thinking about in the 1980s. When they discovered that the stars that were moving around the Milky Way were moving fast enough that if there wasn't extra mass that we couldn't see, they should fly apart, and we don't think our galaxy is doing that. And so they gained this idea that, well, there must be some mass here that we can't see. It's not that it isn't stars, and it's not that it's even gas, because if it was gas, we'd be able to see it absorbing the light from stars behind it, It's just some dark stuff out there. And so I remember as a graduate student being told, oh yeah, there's dark matter, there's like particles all over the place, billions of dark matter particles, they're passing through our bodies all the time. It's here in the room, it's everywhere, it's, this stuff here we can't see. And I thought, yeah, right, sure, there's dark matter. Doesn't make any sense to me. Why can't we change gravity? Can't we make things outward? But actually, it's not as crazy as it sounds, because there are, in fact, trillions of neutrinos that are going through your bodies every second right now. And those neutrinos we know are there because we have detectors that we've detected them. And they're produced in the center of the sun when the sun turns hydrogen into helium. And these neutrinos flow out through the sun, and then they flow right through space, and they flow right through us and the Earth and everywhere else. But we can detect a couple of them and see that they come through. So it's not crazy. One of the problems we have with dark matter, though, is that people have been building detectors to try to do the same thing for dark matter, to detect a couple that are coming through the Earth for 30 years and haven't found anything. So we have a little bit of a problem with finding dark matter particles themselves, but we do see that there's something out there that's keeping stars going in their orbits. So we know that there's a lot of dark matter in the Milky Way, maybe 85% or something of the mass in the Milky Way galaxy is this dark matter particle we can't find. But we have very little or none information about where that dark matter is in the Milky Way. You know, people say, well, maybe it's spherical, or maybe it's squashed towards the disk, or maybe it's the other way, football-shaped, coming up out of the disk, or maybe it's some blobby thing. Probably, we think now, probably changes with time. It changes with distance from the center of the galaxy. It changes when big galaxies go by and merge. And probably it's actually this big lumpy distribution. And so I've been trying to figure out where dark matter is in the Milky Way galaxy. The only way we know how to find dark matter, which is by looking at its motions on stars. And in particular, I've been looking at the motions of stars in tidal streams. And they're good because they're the only stars in the Milky Way where you know not just where they are and how fast they're moving, but also where they were in the past. Right, because they all came in on the same dwarf galaxy on that orbit, and so you can track it through. And that gives you some idea of the potential through, in fact, stars in tidal streams are on their orbits because of the whole history of where they were in the dwarf galaxy, how that dwarf galaxy fell in, and the potential, the gravitational potential of the Milky Way itself. So I have a supercomputer that's volunteered. I'm my own volunteer supercomputer that tens of thousands of people all over the world volunteer their computer time. And I send out jobs to them, and I'll be like, I have this data for a stream over here. Can you try making a simulated dwarf galaxy to go around the Milky Way and make that stream with these parameters and tell me how that went? And then we do that for all of these people and get tens of thousands and hundreds of thousands of people to try different parameters. And that way we find we can find a simulation. This one keeps running, so it keeps running here. These people here are running on their computers. And they're going to find the best parameters for the dwarf galaxy that fell in and made the tidal stream. And my graduate student, Sid Shelton, wrote his thesis doing the following thing, which is to take a dwarf galaxy, run this simulation to make a stream, then give Milky Way at home only the information about the density of stars along the stream and the dispersion of the stream, how wide the stream is, and gave only that information to Milky Way at home, and it was able to recover the shape and the mass of both the stars and the dark matter in the dwarf galaxy that fell in. And so we know the information for that is there. The thing is that we did tell it what potential we used for the Milky Way, and we told it what orbit it was on. So, you know, it had correct information for things that we don't actually know for the real data. But we know the information's there, and so we're working towards using all the different pieces of information in order to constrain all of the parameters that make up where the dark matter is in the dwarf galaxies and in the Milky Way itself, and when it fell in, and what orbit it was on, and so on. All right, so my more recent student, Eric Mendelson, took that the one obvious step further, which is to run that on a set of data for one of the streams called the Orphan-Chenab stream in the halo of the Milky Way. And what I want to say first is that the current understanding of these very faint, small, we call ultra-faint dwarf galaxies that are falling into the Milky Way is that they have a minimum mass of about 10 million times the mass of the sun. And most of that, almost all of that mass is in the dark matter. Okay, so that's the current idea, is that maybe the amount of stars might go down, but there's a minimum mass for what the dark matter of one of these dwarf galaxies falling in is. And when he ran this on the real data, what he got was a factor of 10 less than that. So 10 times less than the minimum that we were supposed to get for a dwarf galaxy. So is that true or not? And my answer is I don't know. I don't know because it's extremely difficult. I mean, the statistical errors on our result are tiny, but the systematic errors, the errors from the things, the assumptions that we made when we made this measurement, I don't know if they're large or they're small. They're completely unknown. And so our next task that we're working on now is trying to figure out how to understand the systematics of which decisions we make when making this measurement are the ones that make a difference, and is there a way that we can come up with a measurement that we can put out there and say, this is it, this is the right answer for, and it's incredible. It's the first time anyone has ever tried to figure out what the galaxy looked like before it fell in and became this stream of stars that we see going across the sky. And so we're the only people who have the ability to even do that. All right. So with that, I'm getting to my conclusion. And my conclusion is the Milky Way is in motion, and it's evolving in time. And what you're supposed to be taking away from this is that small galaxies are falling into the Milky Way. They're being ripped apart by gravity. They're forming star streams if they fall in kind of circular orbits. They form shells if they fall in on these radial orbits. And we've been able to find them and characterize these streams and these shells. And then also when they fall in, they cause these wave-like particle motions in the disk that show that our galaxy is not completely in equilibrium. And it's been kind of a problem for us as astronomers because we've always assumed everything was in equilibrium when we're trying to figure out how much mass is in there or what the shape of the disk is. We always assume that it's some, smooth shape. But we've been given so much data that we can show that these simple models just aren't correct. So our galaxy is in a state of disequilibrium, and we're trying to use streams of stars to try to figure out where dark matter is. All right. And then the bottom line after this is that these advances are being made here at Rensselaer. And I'm going to stop right there.